To all. So today we are assembled here to witness the Viva voce examination of Mr. Rubin Bose. So you will be discussing about its research topic on performance analysis of different deep learning architectures for hand action recognition. So the members for this Viva voce examination is Dr. Arup Kumar Pal, Indian examiner. Professor is an associate professor in Indian Institute of Technology, Indian School of Mines, Dhanbad. Sir's area of expertise is in the area of image processing, multimedia security, data compression, content-based image retrieval, and cryptography. So Sir has more than 85 number of publications in reputed journals and conferences. So another expert, subject expert is Professor Palanisamy sir, professor from National Institute of Technology, Tiruchirappalli. Professor's area of expertise is in the area of statistical signal processing, adaptive filter, and adaptive noise cancellation, array signal processing, detection and bearing, estimation, frequency estimation, image processing, medical image analysis, data and image compression. So professor has more than 153 publications in reputed journals and conferences. So with your permission, sir, now I request Mr. Rubin Bose to defend this research topic. Thank you.
Please continue.
Good afternoon, one and all present here. For myself, I am Rubin Bose, full-time research scholar of Department of Electronics and Electronics Engineering, MIT campus, Anna University, Chennai. I am doing the research under the guidance of Dr. V. Satish Kumar, Assistant Professor, Department of Electronics Engineering, MIT campus, Anna University, Chennai. And my research topic is performance analysis of different deep learning architectures for hand action recognition. Presentation overview, introduction, scope of research, research motivation, research objectives, dataset collection and pre-processing, literature survey, hand action recognition approaches, 6-axis robot manipulation, conclusion and future work, publications and references. So introduction, hand action recognition plays a crucial role in communicating with machines. So it is a non-verbal type of communication with visual expressions such as hand gestures or hand actions. It promotes an innovative, natural and user-friendly way of interactions with machines. It also transmits essential information with both humans and machines. So there are two types of hand gestures are there. One is static mode and another is the dynamic mode. So in our research, we have concentrated on static mode of hand gestures. And vision-based hand action recognition techniques can be performed using two different approaches. One is appearance-based approach, and second is the 3D hand model-based approach. This is the overall block diagram of vision-based real-time hand action recognition system. So here we use a web camera to capture the hand gestures of different people, and the input frames which is obtained through the web camera will be sent towards the deep learning model. So in deep learning model, the hand region will be detected first, and then the respective features of the hand region will be extracted, and the extracted features will be compared with the already trained model. And if the extracted features matches with the features that is available in the trained model, then it will predict a particular output. So based on that particular output, so we send some information to the remote located robot to do some operations. So here we use AWS system to transfer the data through cloud. Scope of research. So hand action recognition has a broad array of applications. So it can be used in human-machine interaction system, then sign language recognition, then robotic device manipulation in industries, then automotive control in autonomous vehicles, video monitoring, surgical navigation systems, telesurgery systems, and virtual reality. Research motivations. So there are several challenges in hand action recognition system. The human hand consists of around 27 bones in human hands and 26 degrees of freedom. And each finger consists of around 4 degrees of freedom, and the wrist consists of around 6 degrees of freedom. So it is a difficult task to recognize the hand since it has a large number of degrees of freedom. Then second is self-occlusion. Some part of the hand might be hidden when we capture the hand region using a camera, and it is also a challenge to predict a particular gesture if some part of the hand regions are hidden. And next is the illumination variations. When we use the real-time camera to capture the images, hand gestures, then illumination condition also plays a major role here. So different illuminations will affect the gestures what it is predicted. Next is variation in hand geometry. So here different age groups have different geometry and different size of hand regions. So it is also a tedious task to recognize the particular gestures. Then uncertain backgrounds. So background is not similar. So it was a main challenge. So what we consider in our research here. So if it is a white background or if it is a single colored background, then the image can be easily extracted. That is what happened in the traditional image processing system. So there, if the background is a fixed one, then it can easily predict the gestures. But when we go for a real-time implementation, so this kind of background elimination is a difficult task. So it is also plays a huge role in the hand action recognition system. Then viewpoint variation. So a same gesture can be captured in different viewpoints. So this image shows that. So it is a single gesture. So it has different viewpoints. So it is also affect the gesture prediction. Then rapid motion. So rapid motion of human hands and the motion of the cameras can also affect the hand gesture prediction. Then computational speed must be high. So when we go for the real-time implementation, so it is also a challenging task. So research objectives. So to collect a hand action data set that can be utilized in a real-time hand action recognition system, and to analyze the performance of a multi-stage deep CNN model for a real-time hand action recognition framework, then to experiment with the different single-stage deep learning architectures for hand action recognition system, also to optimize the parameters for a better prediction rate, to develop a robot manipulation framework using a deep learning based hybrid single-stage hand action recognition system. Research workflow, that is performance analysis of different deep learning architectures for hand action recognition. So it consists of these following modules. So first module is dataset collection. So here we collected two different data sets. One is the standard data set and another is the custom data set. Again, in standard data set, so we preferred two data set. One is a National University of Singapore hand poster data set 2 and another is the Sense 3D data set. So custom data set we ourselves collected from different age groups of people, and the details of this custom data set will be explained in further slides. And data set pre-processing. So data set pre-processing we used resizing. So interpolation method we use here. Then region of index selection. Then train data and test data separation. Then hand action recognition framework can be carried out in this research. It is carried out using a deep learning approach. And here we use two different architectures for that. One is the multi-stage CNN architecture and another is the single-stage CNN architecture. So under multi-stage CNN architecture, we use Faster R-CNN Inception-V2 model and single-stage CNN architecture. So we have investigated around 6 different architectures here in various environments. And finally, the predicted hand gestures is used to control the robot that is present in the remote location. So here we use the 6-axis robot to manipulate it. Next process is the dataset collection process. So dataset collection, standard dataset. These are the datasets that is available in public, and this Sense 3D datasets consist of 1,200 samples, and out of this, 960 samples are used for the training process, and 240 samples are used for the testing process, and it consists of 10 different classes. and the size of the sample is 300 cross 225, and the skin tones is similar. Subjects, so it was collected from only 4 different persons. And the second set of data set is MES hand posted 2 data set. So it consists of total 2,750 samples, and for training we used 80% of the samples we use for training and 20% we use for testing. And it also consists of 10 different classes. So it has 2 scales of images. And again, in this NUS hand post 2 data set, it also consists of somewhat similar skin tones. So it was collected from 40 different peoples, and the age groups from 22 years to 56 years. And custom data set, so MITI hand data set. So these data sets are collected by ourselves, and we preferred different skin tones in this MITI hand data set. And we consist of around 7,500 samples in MITI-HD, and MITI-HD2 consists of around 9,800 samples. So again, 80% of the trained samples are used for training, and 20% of the samples are used for testing. Again, classes we consist of we have around 10 different classes, and the image size of the samples are around 640 cross 480 pixels. And skin tones, we prefer different skin tones, and we collected MITI HD data set that it was collected from 25 different peoples, and MITI HD2 was collected from 32 different peoples. So age groups, so we prefer 7 years to 60 years. Access data set pre-processing. So this flow diagram shows the collection of the data set, and after the collection of data set, so it was sent for data pre-processing process. So here we have resized the sample, and then we go for the ROI selection. So for resizing, we have used interpolation technique, and here when we resized this standard data set, the size of the data set is around 640 cross 480, and we have resized into 300 cross 300 pixels. So this is before resizing, and this is after resizing. And since it is a rectangular image, so when we convert it into 300 cross 300 pixels, the other region is filled with the white pixels. So in order to maintain the aspect ratio. Then region of interest selection. So here we have selected the hand regions by using a label image tool. And after the data pre-processing, then we move for the data split process. So here 80% of the samples are used for training, and 20% is used for test samples. The main reason for splitting the data for training and testing was so in order to avoid the overfitting process. The training samples are assigned for the model to train, and test samples are assigned for model evaluation process. In training process, after the pre-processing, then we go for the training process. So here, as I already mentioned, so we have used 2 different architectures. One is the multi-stage deep CNN architecture, and another is the single-stage deep CNN architecture. So in multi-stage architecture, we have used Faster R-CNN Inception-V2, and in under single-stage deep CNN, we have SSD Inception-V2, SSD Lite MobileNet V2, YOLO V2, RetinaNet DAC, enhanced CenterNet model, and finally we have proposed a hybrid SSR model for hand action recognition. Then after the training process, then the generation of inference model file, inference model file is generated, and the trained model can also be evaluated using the test data sets. The first process is multi-stage deep CNN architecture for hand action recognition. For literature survey, so there were several conventional approaches are there, and deep learning approaches is also there. So Arenas et al. 2017, he proposed the R-CNN, region-based CNN model for hand action recognition process, and Musi et al. 2018 present the Faster R-CNN for hand action recognition technique system, and in this they used VGG16 as the backbone network. Again, Musi et al. 2019 proposed Faster R-CNN plus CPF model for hand action recognition system. Here also they use the same backbone network, VGG16 network. Then Alimjain et al. 2018 proposed a deep CNN model for hand action recognition process, and Lee et al. 2018 proposed Faster R-CNN for hand action recognition. Here they use the selective search algorithm and edgebox detector for feature extraction process. Then Sarochi et al. Proposed RGBD and leap motion sensor along with the gesture vocabulary. They have predicted the hand gestures. And Liu et al. 2016 proposed a hand glove and SVM plus PSO technique for hand gesture recognition process. Limitations. So there were several conventional approaches are used. So the main limitation is the conventional approaches took a large prediction time when we go for a real-time implementation, and the spatial informations cannot be predicted easily. The conventional methods are not suitable for huge data. The computation time is very high in the conventional approaches, and when we go for a huge data set, again the computation time will be very high. So that way we preferred for our system, we have preferred a deep learning approach. So multi-stage CNN architecture, we used a Faster R-CNN Inception-V2 model. The faster region-based convolutional neural network. So this is the block diagram of Faster R-CNN Inception-V2. So here it consists of a fast R-CNN module, as well as it consists of a region proposal network. So once the data set is collected, then we go for the pre-processing, and then we go for the training process. So in this Faster R-CNN Inception-V2 model, so here we used a separate CNN for we used a separate CNN for feature extraction, and here we used the Inception-V2 model for feature extraction process. And the region proposal, again we used another CNN, and here these two processes, feature maps and region proposals, are extracted separately. And after completing this, then we go for the ROI pooling process. So in ROI process, the feature maps and the region proposals will be combined, and then it will be sent towards the fully connected layers, and from fully connected layer it will be connected to a box regressor for localization process, and softmax classifier is used for classification process. So after training, then the same module is evaluated, and it was tested in real time. So how it predicts the hand gestures. So again, this Faster R-CNN, it was trained using 3 different optimizers. One is the Adam optimizer. So it uses landing rate of 0.0002, and momentum, it uses landing rate of 0.004, and RMS probe, we use the landing rate 0.0002. And backbone network Inception-V2, when we compared the previous architecture, what the previous authors they have used in Faster R-CNN, they have used VGG16 network. And when we compared the VGG16 network with the Inception-V2, Inception-V2 has a wider filter banks, as well as it has a deeper filter banks. So some useful information will not be missed here. So this is the backbone network and Inception-V2 architecture as a feature extractor, and this is the block diagram of Inception-V2 architecture. So here we have a stem network. So this is the stem network, and after the stem network, we will have a dimensionality reduction filter first, and then we will go for a deeper filter banks, and then we will go for a wider filter banks. So the reason is, so if you use a deeper architecture, when we go deep and deep, some useful information will also get missed there. So in order to avoid that, so we have used different filters like this. We have used both deeper filter bank, at the same time we have also used wider filter bank, so that no useful information might miss here. So here we used three Inception dimensionality reduction filter, and 5 deeper filter bank, and 2 wider filter bank, and then the layer is connected to a pooling layer, and then we use the linear regression for localization process, and then we use a softmax classifier for classification. Intersection over union. So here we use the deep learning approach, and that too we follow a object detection algorithm for hand gesture recognition. So if it is a normal image processing, so we will calculate the accuracy just by using the accuracy terms. But when we go for a object detection algorithm, so here the accuracy of the system is evaluated by means of intersection over union. So here an anchor box will be generated over every proposed region, and the IOU plays a major role. So intersection over union is an evaluation metric. It is used to measure the accuracy of a hand action recognizer. IO is maintained as unity when there is a perfect intersection between the predicted anchor boxes and the ground truth bounding boxes. So these are the samples you can see here. So when there is a perfect overlap between the anchor box and the bounding box, so IOU value is around 0.92. So in percentage, we can consider it as 92.6% of overlapping. But when if you take this, so it is an excellent prediction, and this first diagram shows it is a poor prediction. So as long as the value of IOU is 0.5, the prediction is true. So if it is above 0.5, then the prediction will be a true prediction, and if it is less than 0.5, for example, this 0.403, so it is a it won't predict the gestures properly. These are the performance metrics of Faster R-CNN Inception-V2 and various data sets for IOE equal to 0.5 is 0.95. So we have took this ratio IOE from 0.5 to 0.95, this ratio. So the hand gestures will be predicted in between these ratios. So here first what we did is, so we have resized the samples into two different size. One is 160 cross 160 samples, and another one is 300 cross 300 pixels. So first, what we did, so we have trained the trained the Faster R-CNN Inception-V2 model using this MITI-HD 160 cross 160 pixel samples, and we used three different optimizers: Adam, RMS prop, and momentum, and we have obtained the results. So average precision and average recall. Then again, we have tested the same for NUSHP2 and Sense 3D 160. So for all this, we get the respective values for average precision and average recall. So in every data set, Adam optimizer outperforms outperforms the RMS prop and the momentum optimizer. So the same trend is also visualized in NUSHP2 160 cross 160 pixels. Next is the comparison of average precision on various data sets for IOU equal to 0.5 is 0.95, then 0.5 and 0.75. So we have conducted different experiments on different values of IOU ranges, and so when we compare these ranges, so when IOU equal to 0.5, so it gives better precision values and it gives better average recall values here. So again, MITI-HD, when compared with Adam, RMS prop, and momentum, Adam optimizer produces better results, and same trend is visualized in Sense 3D and NUSHP2 datasets. So next, what we did is, so we have compared the performance of 160 cross 160 pixel datasets with the 300 cross 300 pixels. And again, we obtained several results here. So here we obtained the average precision for different ranges. So for all detections, then small detections, medium detections, and large detections, and average recall values for 1 detection, 100 detection, 10 detection. So like that, we have calculated several parameters here. Then we also calculate the prediction time. The prediction time is little higher for greater pixels, that is 300 cross 300 pixel, when compared to 160 cross 160 pixel. And the important thing that is when we increase the scale of the image that is used for training and testing, the more features are extracted here, and the prediction will be more accurate when compared to the low scale images. That is for 160 cross 160. You can see here the average precision is 0.769, and for 300 cross 300 pixels it is around 0.794. So the average precision is higher when compared to the 160 cross 160 pixels. So again, we have compared for different IOU ranges, IOU 0.5, IOU 0.75, and IOU 0.5 to 0.95. For these ranges, again, we have compared the average precision values. So again, the better results is obtained for IOU equal to 0.5. 0.5 produces better results when compared to IOU equal to 0.75, and 0.5 is 0.95. So these are the loss curves that is obtained for Faster R-CNN Inception-V2 model. So here, this is the loss curve that is obtained for NUSHP 160 dataset, and this is the loss curve that is obtained for Sense 3D 160, and this is for 300 cross 300 pixels, MITI-HD 300 cross 300 pixels, and MITI-HD 160 cross 160 pixels. So here, as long as the training steps are increased, the loss is gradually reduced, and we also tested that there is no overfitting is obtained here. So this is the comparison of the performance metrics of Faster R-CNN Inception-V2 with the existing model. So here we proposed a Faster R-CNN Inception-V2 model, and this model produces better average precision when compared to Newsy et al. 2019 and Newsy et al. 2018 and other paper MS Faster R-CNN. So here the average recall value is also high, but the prediction time is a little high when compared to the Faster R-CNN Inception-V2 model. But yeah, but the accuracy and the average precision, average recall, and FN score values are still, it is increased. So these are the samples. So once we trained the model, then we have tested in real time. So this was hand gestures are predicted using a live web camera without using any trained data set. Summary of multi-stage CNN: the performance of the Faster R-CNN Inception-V2 based hand action recognition system is reported, and the results of the model tested on the MITI-HD dataset are in correlation with the results of the standard dataset. The Faster R-CNN Inception-V2 model using add-on optimizer results in better performance. That is average precision 99.10%, average recall 96.78%, and FN score 97.98% than the other two optimizers. The prediction time of the Faster R-CNN Inception-V2 model is around 140 milliseconds. So our ultimate aim was, so we have to the Faster R-CNN Inception-V2 architecture, so it produces a better average, better accuracy. At the same time, the prediction time is little higher. So in order to reduce the prediction time, that is our aim is we have to develop a model for real-time implementation, real-time hand gesture prediction system. So for that, if the prediction time is very high, then obviously the speed of the system will get affected. So in order to compensate that, so we have searched for different algorithms. That is the single stage algorithms. It took very less time when compared to the multi-stage architectures. So the next module is the single stage deep CNN architecture. So it is used for hand action recognition system. So literature survey, that is Leng et al. 2019 proposed ESSD plus feature fusion for hand action recognition process, and Visu et al. 2017 proposed a single stage detector. And this single stage detector, they used ResNet as a feature extraction network. And then Othman et al. 2018 proposed a SSD model using a mobile net architecture as a backbone network. Then enhanced SSD, it was proposed by JX et al. 2019. Again, VGG net is used as the backbone network, and King et al. 2019 proposed SSD multibox model, and ResNet and Inception. These two architectures are combined used for a feature extraction process. And Jiang et al. 2017 proposed modified SSD. Again, ResNet is used as a backbone network, and Mo et al. 2018 proposed tiny SSD. SqueezeNet is used as a feature extraction network for hand action recognition. Then Alex et al. 2018 proposed MF SSD, that is VGG net plus ResNet combined they use for the backbone feature extraction. Then Live et al. 2018 proposed Fire SSD model, and residual SqueezeNet is used as a feature extraction backbone network. Then UZ et al. 2018 proposed tiny DSOD for depth-wise dense here for hand action recognition process. Here depth-wise dense block is used as a backbone feature extraction network. And Kobuklu et al. 2019 present hybrid CNN plus ResNet 101 for a hand action recognition process. Again, ResNet 10 is used as a backbone feature extraction network. And Redmond et al. 2016 proposed a YOLO-based deep learning architecture for hand gesture recognition, and Darknet is used as a backbone network. And Pavani et al. Proposed RetinaNet model for hand gesture recognition, and ResNet 50 is used as a backbone network here. And Buan et al. 2019 proposed CenterNet 511, in which Hourglass 104 is used as a backbone network. and Cotiolot et al. 2019 presents convolutional network for hand gesture recognition process, and Sung et al. 2017 proposed RetinaNet model in which ResNet 50 and ResNet 101 is used as a feature extraction backbone network. So we have do the investigation on various single stage deep learning architectures, and due to the time constraints, so I have put a comparative chart here, and we have explained the overall functions of each module. That is SSD Inception-V2 module. So it is the basic single stage CNN model. SSD represents a single shot detector. So this SSD utilizes, in SSD, classification localization of the hand clusters are done using a single forward pass network and the bounding box regression techniques. Here, no need of a separate CNN for both the process, classification and localization, no need of a separate CNN, just using a single CNN. So we have done the process, and here a sliding window will be run over the image on various filter sizes, and based on that we have classified and localized the hand regions by using the SSD Inception-V2 model. So we trained this SSD Inception-V2 model using different data sets, MITI-HD, NUS-HP2, and Sense3D. And optimizer, we used Autumn optimizer, Momentum, and RMS prop. And we have trained this model for 33,000 steps, and we use the batch size 8. And the Inception-V2 CNN model is used as a backbone feature extraction network. The Inception-V2 network consists of 42 layers, and it consists of 25 million parameters. And this replaces the traditional VGG network from the traditional SSD model. And this VGG network consists of only 16 layers, and it consists of 138 million parameters. So since we used the deeper filter bank and the wider filter bank and dimensionality reduction filters, again the training parameters is highly reduced in the Inception-V2 network when compared to the VGG network. And the average precision obtained for SSD Inception-V2 model is around 99.00%, and average recall is 95.40%, and prediction time is 46 milliseconds. So the main drawback or main limitations over this SSD Inception-V2 model is it cannot predict very smaller objects, and another drawback is large number of mispredictions is occurred when we go for the real-time prediction. The second single stage model is YOLO-V2 model. Again, the YOLO-V2 model is trained on the same data sets what I have mentioned earlier, and same optimizers and same training steps and batch size. And the YOLO-V2 model overcomes the limitations encountered by the existing SSD Inception-V2 model. So in YOLO-V2, we used the darknet 19 CNN architecture as a backbone feature extraction network. It enhances the prediction accuracy and speed of computation. So it took only 20 milliseconds for prediction, whereas this SSD Inception-V2 took around 46 milliseconds of prediction. When compared to the Faster R-CNN or the multi-stage CNN architecture, so this prediction time is comparatively very low, and Faster R-CNN it was around 140 milliseconds, but the prediction time is highly reduced in the single stage CNN architecture. So it also promotes the network to operate at lower scales, and still this mispredictions are existing. Then the third model we have tested is that is SSD Lite MobileNet V2 model. SSD Lite MobileNet V2 model. It is a time efficient model, and it is a lightweight object detection model. And here MobileNet V2 is utilized as a feature extraction backbone network, and it is incredibly fast in recognizing the hand clusters. So when compared to the previous two modules, that is SSD Inception V2 module and YOLO V2 module, so the prediction time of the SSD Lite MobileNet V2 model is very, very low. At the same time, there is a little compromise in the average precision and average recall values. The prediction accuracy is poor here. At the same time, misprediction is not completely eliminated. So these are the drawbacks in the SSD single stage models. And the fourth module is the RetinaNet DSE model. The RetinaNet DSE model is also tested on same data set and optimizers and same training steps and batch size. RetinaNet DSE addresses the misprediction challenges encountered by the other single stage recognition models. For example, SSD Inception V2, YOLO V2, SSD Lite MobileNet V2, modules. So here in RetinaNet DAC, we use the ResNet 101 and ResNet 50 as a backbone feature extraction networks. So here we did some modifications in this architecture. That is, when compared to the original RetinaNet, so we have did some modifications in the fully connected layers, and we have replaced the fully connected layers with some depth-wise separable convolutional layers here. And we also used a focal loss function here. And due to this focal loss function, the mispredictions that is occurred in the traditional single-stage architectures are highly reduced here. But there is a compromise in the prediction time. The prediction time of the RetinaNet DAC module is around 82 milliseconds. So this is little high when compared to the previous existing modules, but the misprediction is highly reduced in this proposed architecture. At the same time, the average precision and average recall is also improved. And the fifth module is the enhanced CenterNet module. Enhanced CenterNet module is an anchor-free model that replaces the non-maximum suppression that takes place in the previous single-stage architectures. So in the previous single-stage architectures, so a large number of anchor boxes will be generated over image, and finally a particular, that is the maximum, what I can say, that is the maximum covered region. Only that region will be considered as the predicted image, and the other regions will be eliminated. So this will happen using a non-maximum suppression technique. But in enhanced CenterNet model, so here usually what we do is what this architecture will do means, so it will predict the center point of the CAN region, and based on the center point, it will calculate the other coordinates. So it will calculate the other bounding box coordinates, so that the usage of non-maximum suppression is highly eliminated in this module. Again, this enhanced CenterNet module is also tested using different data sets, trained and tested using different data sets, so as I mentioned earlier, and same optimizers and then training steps and batch size. So here the average precision is little improved and average recall is also improved, but prediction time is reduced when compared to the RetinaNet DAC model, but the prediction time is little high when compared to SST MobileNet V2 model. So prediction time is little high. So this is the limitation in enhanced CenterNet model. But when we go for a real-time implementation, so for example, in real-time implementation, the prediction time must be very, very low. So if the prediction time is high, then obviously the speed of the system will be raised. So to avoid that, so we have to reduce the prediction time. So still there is a scope, or still there is a room for further reduction in the prediction time, as well as the prediction accuracy has to be improved, and also the mispredictions has to be reduced. So that is the reason behind the proposed model. So to develop the proposed model, that is, in this slide you can see that, so large number of mispredictions are there. So actually it is 3, and it was mispredicted as 2, and 3 is mispredicted as 4, and phase is also mispredicted. So a lot of mispredictions are happening. So this is the mispredictions that will happen in the single stage image, single stage detector. So our ultimate aim is, so we have to reduce the mispredictions, as well as we have to reduce the prediction time, and we have to improve the prediction accuracy. So by keeping this in mind, so we proposed a new model, that is a hybrid single stage hand action recognition architecture. So in short, we will represent it as hybrid SSR. So this is the overall architecture of a hybrid SSR module, and here we have a hand dataset collection process, then pre-processing. After that, we have a training process. So in training process, we use the enhanced E-Xception CNN model. So this is the enhanced version of the E-Xception model. So E-Xception model, so it consists of some DAC layers and other things. So this enhanced E-Xception model, so we did some modifications in the original E-Xception module, and this performs better in the feature extraction process. So after the features are extracted, then the features will be connected to the fully connected layers, and the fully connected layers, from the fully connected layers, it will be sent towards the extra feature layers to develop a multi-dimension filters, multi-dimensional feature maps. So for that, we use this fully connected layers and extra features layers, and the output of the multi-dimensional feature maps will be connected to a classification subnetwork and regression subnetwork. So in classification subnetwork, we use the focal loss classifier, And in regression subnet, we use a bounding box regressor as a for localization process. So once this process is completed, then we will allow this feature maps to a non-maximum suppression process. So in this, the particular image will be predicted, and all the other anchor boxes will be completely eliminated. So it is a custom developed model that is enhanced exception consists of 42 layers with 22 million parameters. Is compared with the original exception, it consists of 36 layers with 22.8 million parameters, and we also used a focal loss function here. So focal loss function will highly eliminate the mispredictions. In the traditional single stage detector, they have used the hard mining process for eliminating the mispredictions, but it didn't work well. But this focal loss function, so it will give more weightage for the misclassified samples, and it will add less weight for the correctly predicted samples. So here also we trained this hybrid SSR model for 50,000 steps and batch size 8, and it is also tested on various optimizers. So this is the difference between exception architecture and original exception architecture. Enhanced exception is used as a backbone network. So it consists of around 4 residual bottleneck layers. So this is a residual bottleneck layer, and this residual bottleneck layer consists of 2 separable convolutional network and a max pooling layer. And in the residual layer, we also have a convolution layer. And likewise, we will have 4 different residual bottleneck blocks in the empty flow block, and the middle flow block consists of 10 blocks, and in the exit flow block it consists of 2 layers, and we did some modifications in the number of filters that is used in the separable convolutional layers. And in the original exception architecture, so it consists of only 3 residual block nets, and the E-Xception architecture consists of 4. And in middle flow blocks, it consists of 8 blocks, and here it is only 10 blocks. But the number of filters that is used in the last fully connected layers, that is the separable convolution layer, it is very high when compared to the empty flow blocks. So by doing this modifications, so it gives a better result when compared to the exception architecture. The E-Xception architecture, it has 44 layers with 22 million parameters, and the exception layer architecture consists of 36 layers with 22.8 million parameters. So this is the accuracy speed trade-off of hybrid SSR using MITI-HD dataset. So the average precision obtained for E-Xception model is 99.60%, and for average recall is 98.56%, and F1 score is 99.07%, and prediction time is 12 milliseconds. For other optimizers, RMS prop and STD optimizers, so these are the results obtained, and when compared to the other optimizer, Adam optimizer performs better. And for exception module, the Adam optimizer produces this result, that is 99.30, when compared with the E-Xception model, this value is a little lower. And again, exception module also produces better results when compared to RMS prop and STD plus momentum optimizers. So then we tested the model, hybrid SSR model, with the other data set, that is the standard data set, that is MITI-HD2 data set. So this is the results obtained for MITI-HD2 data set, and the same trend is visualized here also. There is in MITI-HD, it also produces the same trend as similar to the previous one. That is MITI-HD, Adam produces better results, and MITI-HD2 also Adam produces better results when compared to others. And again, in E-Xception module, by using max pooling, so it produces better results. We also tested this module with the average pooling. So average pooling produces low results, but that is not mentioned in the slide. Again, this is tested with the other data set, Sense3D. So this is also a standard data set. Again, the trend is visualized similarly. And the performance metrics of the performance metric comparison of hybrid SSR with other CNN models on MITI-HD data set. So this is the multi-stage CNN architecture that is Faster Inception, Faster R-CNN Inception-V2 model. Then YOLO V2 enhanced CenterNet using enriched hourglass model and CenterNet hourglass model. Then RetinaNet DSC with ResNet 101, ResNet 50. So all these models we have trained and we have analyzed or we have evaluated the results using our test data set for this MITI-HD data set. And Hybrid SSR E-Xception model produce better results when compared to the other module. Faster R-CNN, the prediction time is very high, but Hybrid SSR E-Xception, the prediction time is 12 milliseconds, whereas in the SSD Lite mobile net, so it is produced very low prediction time, that is 10 milliseconds, and the prediction time that is obtained using Hybrid SSR E-Xception, it is very close to that of the SSD Lite mobile net V2 model. And SSD Lite mobile net V2 model, again the prediction accuracy, that is average precision and average recall, is still very low, but Hybrid SSR produce comparatively a higher average precision value, average recall value, and F1 score value. And summary of Hybrid SSR: the Hybrid SSR model is specifically designed for real-time hand action detection and recognition process. Then the performance of the proposed Hybrid SSR model using E-Xception and original exception as a backbone network are also analyzed. The proposed Hybrid SSR model using Adam optimizer outperforms the other optimizers considered in the study. The model is tested on MITI-HD2, newest HD2, and Sense3D dataset. MITI-HD2 is a custom dataset, and these two are the standard datasets. The proposed Hybrid SSR model is more time efficient when compared to the other architectures, and it is only 12 milliseconds for prediction, and it is also highly precise. Its average precision is 99.60% and average recall is 98.56%, and F1 score is equal to 99.07% to perform a real-time hand action recognition task. That is, the value of average precision and average recall plays a major role in real-time prediction. That is, as long as the average precision is high, the average recall also has to be improved. So if the average recall is low, then you cannot predict the images very clearly. So as long as the average precision is increased, again the average recall also has to be improved. So that is obtained in the Hybrid SSR model when compared to the previous architectures. In previous architectures, the average precision is less than this value, but here it is very high. So these are the hand action recognition that is predicted under various environments. So here the elimination condition is poor, still it predicts the hand very clearly. So this is the for single hand action, and this is for multi-hand action. So next is 6-axis robot manipulation using real-time hand action recognition. So this is the end-to-end setup of 6-axis robot manipulation using live hand gestures. So here we use a simple web camera to capture the hand gestures, and it will produce some real-time frames, and that frames will be joined to a Jetson Nano. So in the Jetson Nano, we have inbuilt the inference model. Inference model is by training the different architectures, different deep learning architectures. So here we have inbuilt this Hybrid SSR, SSD Lite Mobile Net V2, then RetinaNet DSC, enhanced CenterNet. So all these modules are tested using this Jetson Nano module. And here the real-time frames, from the real-time frames, the hand regions will be detected first, and hand features will be compared here. So as I mentioned in the second slide, so same thing will happen here. So first the hand region will be detected, then the features will be extracted. So once the features is extracted, then that feature will be compared with the trained model. So this inference model has some trained architecture, so that trained features, it has some trained features, and that features will be compared with the live features. So if these two features matches, then it will recognize a particular hand gesture. And again, we use a custom precise prediction function, that is CPPF. So this custom precise prediction function is for when we go for real-time implementation. So there should not be any misprediction. So we will expect one gesture, but if there is any misclassification or if there is any misprediction happens, then it will affect our aim. So So what we did is, so we incorporate a custom precise prediction function here. So we will allow some continuous 10 clusters of same samples, uh, same class samples for continuous 10 frames. So if it predicts that, then it will detect the particular cluster, and then it will send the information by means of a cloud. So here we use a MQTT protocol for transferring the data from the Jetson Nano board to Raspberry Pi, and this Raspberry Pi will be incorporated in the 6-axis Nurio 1 robot. So this is it is inbuilt there, and we use the AWS protocol for transferring the data, and the data are transferred. And once the data is received by the Raspberry Pi 3B, then it will do some particular task what we have assigned clearly in that robot. So this is the setup. So what we have used. So we used a web camera, and we have a Jetson Nano board here, and this robot Raspberry Pi board is inbuilt there. So this is the live fan cluster. So it will predict the live fan cluster, and the robot will do some pre-defined task. So these are the angle details about the robot. So it is a 6-axis robot. So 6 angles are mentioned here. So here the system recognized the Guster 4, and this is tested using hybrid SSR model. Guster 4, and the robot will do a particular task that is assigned for that particular cluster. So this is for another cluster. So this is the other one. So totally we have around 10 clusters. For a sample, we have incorporated only 3 demos here. And summary of performance metrics of various deep learning models considered in the study. So here, hybrid SSR E-Xception module produces better results when compared to the all the other deep learning architectures, single stage and multi-stage architecture. That is 99.60% average precision, and 98.56% average recall, and 99.07% upon score. Then the prediction time is 12 milliseconds. So we have tested this with the different platforms. So we have used NVIDIA Titan X for prediction. So when we use NVIDIA Titan X, it produces 12 milliseconds for prediction, and for Jetson Nano, NVIDIA Jetson Nano, it produces 195 milliseconds. And if you use Raspberry Pi instead of Jetson Nano, if you use Raspberry Pi, it took 68 milliseconds for prediction. And SSD Lite MobileNet V2, it uses it took 10 milliseconds when we using the NVIDIA Titan X GPU, and for Jetson Nano processor it took only 166 milliseconds, and Raspberry Pi 3B it is 670, and for all the other architectures the prediction time is very high. So when comparing hybrid SSR with other modules, so it has better accuracy when compared to other models. It has somewhat similar prediction time of the SSD Lite MobileNet V2. Summary: the 6-axis robot manipulation using real-time hand clusters are performed. The prediction accuracy and prediction time are tested for different deep learning models. The proposed hybrid SSR model results in better prediction accuracy, average precision 99.60%, average recall 98.56%, and 91 F1 score is 99.07%, and prediction time is 12 milliseconds, and nearby prediction time of SSD Lite MobileNet V2 model, which is around 10 milliseconds. Therefore, hybrid SSR model is more compatible for a real-time hand action recognition. Okay. Conclusion: the Faster R-CNN Inception-V2 model using Adam optimizer resulted in obtaining better performance metrics. That is average precision 99.10%, average recall 96.78, F1 score 97.98%, and prediction time is 140 milliseconds. So it is a multi-stage architecture, and SSD Inception-V2 is a single-stage architecture. It produces the prediction time 46 milliseconds, and average precision 99.00%, average recall 95.40%, F1 score 97.17%. YOLO V2 model produces average precision 99.10%, average recall 96.70%, F1 score 97.80%, and prediction time is 20 milliseconds when compared to other optimizers. The Adam optimizer produces better values. The performance metrics obtained using SSD Lite MobileNet V2 model with Adam optimizer produces the average precision 98.74%, average recall 94.11%, F1 score 96.37%, and prediction time is 10 milliseconds. In the Dataset DSC model, average precision 99.21%, average recall 96.99%, F1 score 98.10%, and prediction time is 82 milliseconds for ResNet 101. And in Retina DSC, SGD with momentum optimizer produces better value when compared to other optimizers. Then enhanced centered model, average precision 99.22% and average recall 98.20%, and F1 score is 98.71%, and prediction time is 30 milliseconds. Here the Adam optimizer produces better values when compared to other optimizers. The performance metrics for hybrid SSR modelers, average precision 99.60%, average recall 98.56%, and F1 score is 99.07%, and prediction time is 12 milliseconds, obtained by using the custom developed model. And it is better suited for real-time implementation. Picoscope, a real-time hand action recognition system using reinforcement learning concept with minimum training data will be developed, and the hand action recognition based on 3D model is also developed. Then references. So these are the journal publications, and we have published 3 papers in 3 different journals, and 2 more journals are in communication. In book chapter publication, in conference publications. If you have any queries, you can ask.